Thanks for the introduction. I'm thrilled to present the work that we've been doing to you this morning. We've been working on a new programming paradigm called Prorogued programming, which I'll talk about today. So let's talk about motivation first. One thing radically changed programming historically, and that was the introduction of interactive computer systems, where you could type something and run it and get results. So that dramatically revolutionized how people program, because before that you had to think about a problem through and then dump what you have thought about into a representation that a computer can understand. Interactive systems change that because they change programming to a process of implementing something, running it, testing it, trying it out, fixing the bugs, and doing it over and over again and making the thing more and more complete. But we can do better. So one issue in the mainstream programming languages is that they force abstraction shifts upon programmers. Let's illustrate that with an example. For instance, let's say I want to write an application that gets an email address from the console and sends a canned email message to the email address, like a spam. And we want to also validate that email address syntactically so that we don't just try to send an email to just a random string. So I start writing a program. As you can see, we read the email address from the console, but now it's the time to validate that address. Unfortunately, as you probably know, if we want to use a regular expression here, we now have two problems. So we either have to put up the current task that we're doing on the shelf, go back, implement that validation function, and come implement the rest of the logic, which is distracting. There is another option, which is to implement a stop. A stop will require writing a signature, and probably in safer languages like Java and C#, you have to even think about the body of that stop, because the compiler worries that you haven't returned a value on all code paths. So you have to fight the compiler to just get your program running. And this is distracting. Even just moving around your source file and implementing that stop is going to be distracting. And anyway, so that's our best choice. If you actually want to run this program and see experiment with the behavior of your high-level main function, then you actually have to even think about the return value of that stop, because then you wouldn't be able to test the logic of your higher level function. We go and continue implementing the function like this, which wasn't obviously the best solution. And it is well known that shifting abstraction is distracting, and distraction hinders programmer productivity. This is why programmers should work in quiet environments, because programming is really a task that relies heavily on short-term memory. Context switches can hinder programmer productivity a lot. So I'd like to highlight a quote from Paul Graham here. He really characterizes one of the most important features that a good programming language should have. Programming language is not just a method for expressing a snapshot, is essentially a memory dump of what is in your head right now after you have solved the problem in a representation that a computer can understand. It is a framework, it's a platform that enables, just like a human language, enables you to think about your solution and then go and sketch out your solution, implement it, refine it, and make it increasingly complete. So with that in mind, I'd like to point out some of the goals that we had when we designed Prorogued programming. Our first goal is obviously reducing abstraction shifts, which, as I said, is important because it improves programmer productivity. Our second goal is to align programming languages with natural thought process as as opposed to letting the compiler tell you what to do and what not to do. The third goal is to aid top-down design. Top-down design is important because it's a natural way to solve problems. If you focus on the high-level solution first and then work out the details later, you'll have a much better understanding on what you want to implement. And bottom-up thinking might lead you to a point where you don't want to be, where you decide that your high-level solution wasn't correct at all. And now you have a lot of wasted effort. Our fourth goal is to promote iterative refinement, to make it easier for programmers to work out a program from a partial state to a more complete state, and facilitate natural workflow as in software engineering workflow, to make it easier for teams to collaborate and people to collaborate. So what is prorogued programming? Prorogued programming is a new programming paradigm that gives a programmer the ability to specify some pieces of program as prorogued, and it's not just from an implementation sense, it's also from a design sense. And let you experiment with the partial implementation that you already have and refine it iteratively to get to the point that you want to be. How it works, we introduced a keyword called prorogue to the language. This keyword can be used to annotate function calls. So let's go back to our mail sender example. Here we have annotated that it's valid email call with the keyword prorogue. And as you see, there's no stop or anything else here in our program. All we have is that call with prorogue. There's no signature for his valid email, nothing. So what happens if we run this program? That prorogue annotation tells the compiler that this function may not exist. And it's okay that it doesn't exist. So the compiler goes and compiles this program as if it were a dynamic language. But there is another problem that even arises in dynamic environments. And that's, what if the execution reaches that point, that function call? We don't know how to handle that. And actually, as you can see in this example, some programs might depend on the return value of a function that doesn't exist to continue execution. So how do we handle that? The simplest way is just to ask the user. We ask the user what would be the return value for is valid email call given the actual argument that's passed to that function at the time of execution. And the user can return a value. But there's a problem. If we ask the user all the time, then the user will be, the programmer, which is the user of our programming language, will be upset because he has to answer a lot of queries. The way we handle that is by caching the queries based on the argument values. So if you run this program once and then give an email address as the input, we cache and return true for his valid email. We cache that true value, and we persist it on disk, actually. So if you run it again and test your program with the same input, you never get a query. So that's essentially the idea of prorogued programming. There's a process that we call reification that's basically a dual to prorogued programming. It's a natural way to make prorogued programs more complete. The reification process basically removes the prorogue annotation from a function call, and using the I/O store that we collected during runs, we can basically reconstruct the basic structure of a program that behaves as if it wasn't prorogued. And you can use that as a stepping stone to make your program more and more complete. And the most interesting part is the last line. We return prorogue. Prorogue without a function to call is just a syntactic sugar for calling the function with the same name using the same arguments. So what happens is that if we didn't know what to do with that, we can still prorogue. Of course, that return prorogue can be used in any function, not just a just reified function. And that's how you iteratively build up a prorogued program and make it complete until you remove all prorogue annotations. We can generalize, and we have generalized prorogued calls to types. So you can annotate objects with object creation statements with the prorogue keyword. Here, we don't have that temperature service at all. So this is a part of a program that depends on an external web service to get weather information and display it in the UI. And we haven't decided on what web service we're going to use yet. So we create an object that we don't have at all in our program and set the API key to some value. And it essentially creates a property on the fly. The same thing happens for current zip code. What's interesting is that the third line doesn't have an explicit prorogue annotation. But the compiler, since it knows the type, knows how to dispatch that method. Of course, if the temperature service class existed and we had a getTemperature method, at that point, the compiler would just dispatch it to the concrete implementation of that method, not prorogued dispatcher. Also, the other thing to point out is that this getTemperature function doesn't get the zip code explicitly, but we have zip code as a property of the object that we created. Since that object has a state, that state is taken into account in the cache that we use to return values. So you can have different return values based on the state of the object at that point in time. So if you run it on one zip code, it doesn't return 10, and the other zip code will return 20, for instance. Moving on, we have articulated some principles that constitute a prorogued, what's called a prorogued programming language. The first principle is the ability to prorogue concerns, to make it easy for the programmer to define some parts of the program as incomplete and defer it for later implementation. The second principle is interesting. We call it hybrid computation. When we set to solve the abstraction shift problem, that was our goal. But we realized that prorogue annotation doesn't serve just as a way to tell the compiler not to worry about that function. It's essentially a way to express as a first-class member of the programming language, not as a debugger extension, not as an IDE extension, inside the program, that this part of computation is not coded inside the host language. And if you think about it, the human that's returning some value is part of the computation itself. It could be a spreadsheet instead. It could be a web service, a crowdsourced system. So it's essentially a way to extend the host language and provide a seamless integration with outside computational sources, one of which is a human. And the third principle is executable refinement, which is the process that we go through to make the prorogued program more and more complete over time. So let's talk about some of the other applications that prorogued programming might have. One interesting application is shadowing while debugging. Let's say you are coding something, you have coded something, and you run into a problem. Here we have a web service that basically sells videos. And we want to redirect users that have successfully paid to us. But the problem is we are debugging something in the program, for instance, that URL generation process could be buggy. And we don't want to mess with that web service because it's a credit card service and it's a pain to test that kind of stuff. So we simply temporarily add the prorogue annotation to that try charge method. And since we explicitly added that, the compiler will warn us that this method exists. Why have you prorogued it? But it's just a warning. It will run it and dispatch that try charge method with prorogue infrastructure. So you can temporarily return true. Or actually, if you have developed this program with prorogue in the first place, you already have that value. And your program will continue execution using the value that you had during development. And you can test the rest of your logic seamlessly. There are a few other applications that I can talk about. Essentially, one of the things that prorogue enables is an easy way to mock resources. For instance, if you have a database or you want to read Facebook news feed, you can mock that stuff and just call using prorogue. And it's better than the current mocking systems in some ways, because if you want to use the contemporary mocking frameworks, you have to think about how what's the process of getting the return value x from the argument y, and in prorogue it's just running it and giving it a couple examples, and it will work out itself. The other obvious example is automatic unit test generation. I mean, how many programmers like writing unit tests, even though they might be necessary? So as we collect the unit tests during program construction, the examples, we can generate unit tests from them. Another use case is evolving APIs. Let's say you're working in a team that's a client to an API, and the other team is working on the server side of that API. But the interface of that API is not fixed yet. So prorogue lets you experiment on the client side to figure out what you need in that API. This is actually an instance of proroguing design. One might say that you should write an interface first, but really, sometimes you don't have any idea what a good API looks like. And prorogue lets you figure that out and then go implement the concrete interface, which is going to be fixed probably for years. Another example, as I said, is crowdsourcing. Prorogue could serve as a mechanism to enable shipping of an application to a bunch of users and have them collect input-output examples, and without writing any code, build up a table of input-output values that makes your program run, and you never encounter another prorogue query again. Of course, there are some other applications, like, you can deploy programs that aren't complete yet with prorogue annotations in them with a database. For instance, let's say you have an application that's supposed to be launched in 100 languages, but you need English fast. You can either hard code the localization function, or you can just write a function that returns a value based on the word that's given and the language, and it returns prorogue. And at runtime, you give it to a bunch of users, and they translate for language 1, and it will be in the cache, and you simply ship that program in that state to your users. Of course, it might not be the best thing to do, but sometimes it's necessary. It reduces the risk of software development. So we believe prorogue can change the way people program. We have worked on a prototype in C#, but we'd like to see it implemented in lots of other languages, and most notably JavaScript. We think it's going to be very exciting to have something like this in a JavaScript environment, and we'd love if you could help us with that. So I'd like to thank you guys for listening to my talk.